In the previous video, we looked at how data from software gets available or becomes available for downstream purposes like analytics. And the last category that we looked at was the fact that the software doesn't actually provide any help at all. So it does nothing effectively. So it's just recording all the dimensions data in standard operations in the database, and for facts it's just appending everything, right? So for this category is what you would need to spend a lot of time in the real world, because most software applications are belong to this category, right? They don't publish a service to allow you to pull data for. Neither do they oblige to call your APIs to publish data to, right? So for this do nothing category, you'll have to go through this process of data extraction. As the name suggests, data extraction is just the act of extracting data from the database. From the software really, but the software internally uses a database like we spoke about. So yeah, you're going to read from databases and you're going to read at periodic intervals using queries. That's a very common way in which you can extract data. Typically, the query you would use would be affixed with a timestamp, because you want to read continuously, right? The common case is you want to read newer and newer data as it gets produced, but you don't want to waste the time to read the older data that's already been consumed by you. So in which case, you provide the query, issue it against the database, use a timestamp column, right, which will allow you to identify newer records in that specific table, so that you can pick up only the newer data sets. So for instance, if you were doing this on the train departure facts table, right? The example we saw was train 12456 departing from Pickenhead Junction at 4:45 p.m. You would have a bunch of those facts, right? So now you want to consume that to understand how many departures happen, as an example, on a daily basis. So you would come and execute the query for yesterday, you get all of the information for yesterday. When you come and execute the query for today, you don't want the data for yesterday, because you've already done that, you've already computed the answer. So in which case you would say, give me, so you do an SQL query which says, select all the train departures that have happened from this table where actual time of departure is greater than midnight of today morning, right? Midnight of today, effectively. So that timestamp allows you to optimize a bit how much you're reading relevant data from the database. But if that timestamp was not available, or worse, if the backend table was being updated in place without changing anything else, right? Then even though you might use the timestamp column to get recent data, you might lose out on updates that have happened in a table which pertains to past data, but that has not changed the timestamp, right? So let me explain in a different way. In that train configuration table, dimension table, which has the available classes, we spoke about how in updating the available classes to include first class, because a new reg is introduced, you could do an in-place update, or you could do an SCD type 2. If you did an in-place update, if all you did was just change the available classes, how would somebody reading from the database to extract what's changed know about it, right? In that example of that table, there is absolutely no way to know about it, because there's no timestamp column. So the only way, right, to deal with it without losing data, without worrying about data loss during extraction, is to read the entire thing again, right? Read the entire table from scratch, all the trains configurations. Then you compare that entire dump of the train table, right, train configurations table, with the train configurations table dump that you took from yesterday. When you compare, then you'll see, oh, the Pickenhead Superfast Express available classes field has changed. That's how you would know that a change has happened. As you can imagine, this is super expensive if the dimension table is large in size. So imagine if the dimension table was set of all customers of IICTC. If I have to go through this process to figure out what is a new phone number for somebody. Such a waste of effort. Anyway, some software is designed like this. There's absolutely no way around it. Or the other approach you take is, I don't care if it's changed. Yeah, that's okay if it's changed. If there is no timestamp column, then I'm going to just let it go, right? Which is resulting in loss of data. So this process of taking the entire table, comparing it with the version of the table from yesterday and figuring out what's changed, that's called snapshotting, or that's also called master dump, right? Because you're taking a dump of the master, dump of the dimension. The dump is basically all the rows, right? And then comparing it to figure out what is the delta. Delta meaning what is the incremental change from yesterday's dump to today's dump. So that's the way to deal with tables which are known to have in-place updates. The best scenario is if SCD type 2 is used, or there is another tool which gets used, which is called as change data capture, and this tool needs a configuration in the source database to be used correctly. So let's break it down, right? In the world of SCD type 2, I've got individual rows of information. Those individual rows of information, let me go back to that example, have an effective start date and an effective end date. So if the source has been changed because the software is recording a new update to a piece of data that's there in the dimension table, it's going to change the effective end date for the current version to be as of today, so that that record is closed, that record is no longer valid. It will open a new record which has the same primary key and have an effective start date which is as of that date. We know that already. Which means if I have to figure out what's changed in a dimension table, and that table has an SCD type 2 structure, all that I have to do is just record what was the last date for which I queried successfully, use that as the effective start date, and query all the new records for effective start dates greater than that particular date for which the last query ran successfully. Right? Simple. So I just use this timestamp and get all the new changes that have happened. That's SCD type 2. And for in-place updates, right? For in-place updates, like I said, we have an option to deal with the data loss by taking an entire dump, etc. There is a specific tooling that the database can support. Not all databases support this. Some do, and the ones that do are the ones which are most popular, like Postgres, MySQL, IBM, Oracle, Microsoft SQL Server, etc., right? MariaDB. So all of those support this. So it's quite common to find this approach available for dealing with in-place updates tables. Is this concept called as change data capture. As the name suggests, what this option allows the database to do is record every change that happened to the data, including in-place updates, including appends to facts, etc., as a separate SCD type 2 style data capture in a log. I'll phrase it in a different way. So every change that's happened, it's as though you're doing an SCD type 2. It's changing that particular, rather it's recording that particular data, the new form of the data, and entering it as a fact event in an operational log, in an operational file that the database maintains. So as far as the database operations are concerned, every single one of those data changes is an event. So to that operational log file, it just appends all those events. And therefore, if you want to find out what's changed, right, you can just look at the operational log file and understand what is the change that happened to a specific data element. Some of these change data capture or CDC options in some of the databases also allow you to log the before image and the after image. What that means is, like in an SCD type 2, you've got the previous version of the record, which is no longer valid as of today because you've made the change today, and the new version of the record, which is valid from today, right? So the version which is no longer valid is called as the before image. It's after you took a photograph of that particular record, so that's why it's called the before image of that record, and the after image of the record is the one that's valid from today. So some CDC tools of some databases actually support the record in the operational log of the before image and the after image. So in which case it's even better, right? Because you can just sequentially read the operational log, you'll know what is the before image, what is the after image of that record, and you can decide to do something with it. So this pattern of logging events as they occur without changing any event, right? Without changing any data in the operational log is what's called as event sourcing. And this event sourcing is a very, very important concept to understand for all modern internet software designs as well. While obviously it's applied in the context of change data capture, so that you know what the in-place updates are. That's how we introduce this concept in this lecture. The concept of event sourcing is much broader than that, right? So let me give an example of how it's broader. Any single API call made to any cloud native software, made to any internet software, logging that particular API call, right? Who made the request? When did they make it? What was the request body? That's an event, right? Then the software could query a backend database, could go look up some other data from some other dictionary, and then stitch a response together. And each of these could be different microservices, which means they themselves are producing data. That data is also being recorded as part of an operational log. That is also an event, right? And then the software then stitches the final response and then provides the response back to you, sometimes synchronously, sometimes asynchronously. That event is also logged, right? So in that set of events which are logged, the event sourcing ensures that you've got every single one of your data exhaust across your entire software available for further analysis at a later point of time, right? So this paradigm of treating everything as an event and then looking at ordering those events, right, to understand what is the impact on your software is actually a very critical foundational principle for all modern internet software. So if you take the IITC example, if I use this paradigm for logging every single part of every single event for every single subsystem within IITC, I can use those events to reconstruct the IITC business. I don't need the software anymore, right? I can just look at that event stream. I can come back and reconstruct what was the IITC business for that particular day. By business, I mean what is the revenue, what are the number of payments, what customers, what tickets, what bookings, what train departures, what station cleanups, everything. Because those events are all sourced as part of that operational log, because I'm following event sourcing paradigm. So when you design cloud native software, remember we spoke about cloud native being observable, manageable, etc. One of the ways in which you do it is by using event sourcing as a paradigm. So your software design can consciously choose to emit events for every single salient business scenario that you are encountering within your software, right, within the code. By doing that, every single state change, every single business scenario, you emit an event and let those events be collected in a message store, in a message stream, or in an operational log. And that becomes very useful for analysis later on. Okay, that's about event sourcing. Let's come back to what we just spoke about, data extraction. You look at data extraction as the only way out for software which does nothing, right? Because it doesn't actually publish a service, or it doesn't publish data to your service. So therefore, you have to go and get the data from it. So you can either read from it using queries, using timestamps, or you use full dumps of the master, compare two full dumps and understand what's changed, what's delta, what's incrementally changed. Or you can use change data capture, right? And change data capture as a tool is available for you to go look at in-place updates and then look at those updates as an event stream so that you can reconstruct what exactly happened. Or the best scenario is the software has actually already done SCD type 2, in which case you just read SCD type 2 using queries, right? That's easy. what do you do with all this data that's actually extracted? Notice that the CDC data by itself is not yet ready to be consumed for analytics. You still have to do massaging, you still have to do processing. So let's look at options of where to store this data first. Right? In the next week's lecture, we talk about processing techniques. Where do you store this CDC data? Where do you store the event source data? Where do you store the extracted data? Right? For understanding what the different storage options are, firstly, you have to understand what are the different storage patterns. Like what we spoke about as software which powers business processes, which stores the data that's created as part of the business process. That kind of software falls under this category called as OLTP, or if you look at the expanded form, it's online transaction processing, right? So the discussion that we had so far on sources and how the sources use CRUD to store changes in database and how you extract from the database, etc. That all is in the world of OLTP. The word online refers to the fact that the software is always available. It's on the internet and it's always available. Like by internet I mean not the World Wide Web, right? But on the LAN network, right? In your enterprise, within the private network, right? Even that's referred to as what's called as online. Online here refers to the availability, right? The software is always available. Like I don't need to use a CD-ROM or a floppy disk or some of those ancient technologies to come and insert into your laptop and only then it becomes available. That's not it, right? It's always available, addressable through a network, through a URI. Yeah, so that's online. Transaction refers to the fact that it's a business process which is recording a fact, which is recording an event which is crucial, right? Which is critical for the business, right? That's why it's called as transaction. It's not just any event. It's an event which is crucial to the business. So the word transaction is used in this context. Then processing refers to the fact that the software is responsible for processing the transaction, for processing that event, that fact, and doing something with it, right? Meaning record that event and do a payment, right? In the world of ticket booking software, the transaction is the ticket booking and the payment information and the train departures and all of that, right? All of those are transactions. And then the processing is the processing of a ticket booking to record the fact that you made the payment and that there's a reservation. All of that is processing, right? So the entire thing is called online transaction processing. In contrast, for analytics, there is a different class of software which are specialized for analytics. Those are what's referred to as online analytical processing, or OLAP. So OLAP is meant for analyzing historical data. Therefore, you can then use that data or the analysis outputs to build models, to build reports, to build insights about the business, etc., etc. So the distinction between OLTP and OLAP is the fact that OLTP is meant for real-time transaction processing. Typically, the transactions come in very high velocity, and they also come in singly meaning one item at a time, one transaction at a time. And each of those transactions need to be processed in very quick time, so low latency processing. So the way to think about online transaction processing is high volume, low latency, massive concurrency. You have multiple transactions happening at the same time. So typically, OLTP systems are benchmarked and commonly measured based on transactions per second as the metric. TPS is the abbreviation that's used there. Whereas in the world of OLAP, you're analyzing historical data. The historical data could be so huge that there is no expectation you're going to do that in 1 second. Forget about multiple such analysis happening at the same time. So here, the complexity is in the nature of the analysis, and you're not expecting real-time answers. You're not expecting interactive answers at all. Sometimes it could take days, sometimes it could take weeks. So this kind of a system, the OLAP kind of a system, is optimized for batch processing, long-running jobs, right? And the complexity in the workload is specific to analysis, not transaction processing, right? I don't have to deal with multiple different systems, handing it off and making sure the reservation is happening. None of that, right? In analytical processing, it's all contained. I have to do analysis of very large data sets, looking at multiple data that's within that particular system. I don't have to talk to multiple other systems, typically, right? So that there's a big difference there as well. So OLTP storage systems are typically databases like we spoke about. OLAP, on the other hand, has many different options. So OLAP is typically served by a lot of different options based on what you want to do, right? At the most simplest of scenarios, you can think of analyzing historical data that's placed in files, right? That's typically the case when you start off with small data, not big data, and small data is available as files, let's say on SharePoint or on your laptop or your desktop, and you start doing analysis on top of it using Python. Right? That's typically what happens. So that's possible, of course. In which case the OLAP is nothing fancy, right? It's just simple files. You have to worry about still how the files are organized, how are they stored, what is the nomenclature, how do I know which file to look at, etc., etc. But that's all in your head, right? It's all in the head of the designer, the developer, the analyst. It's not facilitated by the OLAP system itself. The second example of OLAP storage that's possible is what's called as a multi-dimensional cube. So think of a cube, right, as having 3 axes because it's cubes, right? It's 3 axes. But now instead of 3, think about it multi-dimensions, 100 axes, 1000 axes. So then what you're really doing is organizing data along the different axes in that cube. Then you can then come and ask questions which look at various values of a specific dimension, of a specific axis, and based on those values you want some answers. So let me take an example. Let's say I want to count number of trains that have passed by Bikaner Junction. That's the answer that I want in a day. I could organize the data by train departures, but that's not going to be enough, right? That just talks about departure. Whereas I really want the factual data of every single train stop, not just departure, right? So let's assume now we have a table. Every single train, when did it stop at a particular station, when did it depart from that station? So that factual table is available for me. I could lay that down in 3 dimensions. The first dimension is train number, right? Train number 12456, 12457, etc., etc. So I've got, let's say, 10,000 trains. So I've got in that dimension 10,000 data points. On another dimension, which is train stations, I've got a whole bunch of train stations, right? Like a lakh train stations in India, as an example, assuming. In the third dimension, I've got time. Right? Like time is dating back over many years. So now, in this 3-dimensional axis, I lay down my entire historical data. Now I want to answer the question through Bikaner. How many trains passed by? So we want to know. Let's say we restrict this query to only yesterday, right? So what am I doing? In this cube of data, massive cube of data, I've picked one time entry in the time dimension, one station entry in the station dimension, but all trains, any train that passes through that. So it's as though I've taken this 3-dimensional data and projected it onto the single dimension of trains by making the other 2-dimension values constant, right? Which is yesterday on the time dimension and Bikaner Junction on the station dimension. So once I do that, then all I'm doing is just count on the train dimension, right? So this query in a multi-dimensional cube is super fast to do. There are specific technologies which provide this functionality. Granted, those technologies are legacy now, they're kind of old school because there are a lot of other options available for doing the same thing on top of a data lake, on top of a lake house, etc. But this is one of the earliest OLAP specialized technologies that came about. Alright, the other example of multidimensional cubes query pattern that it optimizes for is rolling up a dimension. So let's say, for instance, the time dimension that we spoke about for this train departure data is on a daily basis for the last 7 years, right? So 365 times 7, that's the extent of number of points that are there in that time dimension. But I want to answer the query, how many trains have passed by Bikaner in the last 1 year, right? So to do that, I need to mentally map myself to querying for the last 365 days individually, which could be problematic, right? Because I have to write those kinds of queries in syntax. Multidimensional cubes are very good at rolling up. So if I've set up the time dimension to say, look, these days that I've just defined as values, they actually roll up into a week. They roll up into a month, which rolls up into multiple months, roll up into a year. So if I've set up that hierarchy as part of the definition of the cube, so I can just simply come and ask the question, give me those trains passing by Bikaner for the year, it will break it down appropriately to the raw values, the raw data sets, which correspond to the individual daily data, so that it maps correctly to that year. So cubes are very good at doing that. Alright, so that's cubes. Then the next examples are data marts, data warehouses, data lakes or lake houses. We will take a look at this in the concluding video for this week, in the next video. And then in the subsequent lecture, we will spend a lot of time talking about how data lakes are built out, how lake houses are built out, what does it mean to process data in a data lake, etc.